Okay, so what we're going to be presenting right now is the ping of that attack, how it takes place in a Ubuntu Server 16.04 version. So what we're going to do is first to show the attack, right? So we're using HTOP, which will allow us to see the CPU utilization in real time of the victim's machine, and we're going to be sending now the the ping of the attack, and we're going to be using the F flag, which stands for flood. So we're going to be sending a flood of ping requests with a maximum packet size, and we're going to see how actually that impacts the CPU utilization. Well, we're going to see that it's near like 60%, right? So how do we prevent that from happening? Well, first of all, we want to have a realistic scenario, meaning that we want to first run our web application, right? So what we do first is to make sure that we are rerouting, right, any packet that's coming into us, right, any incoming packet. And what we want to do is to say that any incoming packet, we want to make sure that first is based on TCP or is using the TCP protocol, and it is target the port 80, which is the HTTP port, and then we want to redirect that packet to our internal port 8080, which is where our application is running. If we do that, then we should be able to go to the login like so. But obviously we need to run the application. So for that, we're going to be using PM2, which is just a package that allows us to start our applications in background mode, or as if it were to be daemons, right? So that they don't block the console. So in here, we're going to start the application, and then we will see that it is actually, well, obviously we need to use HTTP. It is actually working, and it's connected to the database and everything is fine. But we still have the problem that we are vulnerable to the ping of the attack. So how do we prevent that? So basically the configuration, as well as using, again, is IP tables, right? So IP tables, and what we're going to say here is that, okay, so first we want to say the following. We want to append an input policy, let's say, that is going to be using for incoming packets that use the TCP protocol on port 22, and we want to make sure that that is the case, meaning that we want to only accept TCP packets coming into us that are directed to port 22, which is the SSH port, which is important for SSHing into our server remotely. We also want to make sure that also that applies for the HTTP, right? Anybody can access our website through HTTP, and anybody should be able to access also our website through port 8080, which is where the port of our default application. At the same time, we want to make sure that we are accepting also packets from our own local host, and so that will be 127.0.0.1, and then we want to accept every kind of like request that's being made there, so that in the end we can set a default, let's say, policy for the inputs. And so by default, we want to make sure that anything that's coming into us is being dropped. If we do that, and if we see the IP tables here, we're going to see that we are accepting any kind of SSH connection to us, any HTTP connection, and also an HTTP connection to port 8080, as well as any kind of request or packet that is being sent within the local host, right? And we're doing this because we want the MySQL server, MySQL database, and then the application that is running to be able to connect with each other, right? Because we are actually dropping any kind of input. And so if we don't do that, if we don't accept also localhost packets, then we would also be kind of having a problem with that connection to the database, basically. Now what we do is to do PM2 logs. What we're going to do now is to say that we want to stop the application from running, and then we want to start it again, right? Start 0. And then we're going to do PM2 logs, and we're going to see that we're connected. If we do that, then yes, we should be able to access the application, but at the same time we should be protected from the ping of that, or from the ping of that attack, right? And so if we do that, well, we can see that yes, the resources are not being impacted actually at all. Like, it's literally maintaining 0%. And so this is actually the basic way and the fastest way, let's say, to prevent the ping of that. Okay, so the next attack is going to be the Smurf attack. Now, the Smurf attack is based on the attacker sending ICMP packets to the broadcast, spoofing the IP address of the victim. Now, once that happens, if that happens, then the broadcast is going to send this echo request to all of the computers connected in the LAN, which in this case would be computers with IP addresses 10.02.10 and then 10.02.14. And we're gonna see that like in a few minutes, or in a few seconds actually. And then these machines are going to send echo replies to the victim machine, generating a DDoS attack, which is actually something good, or something actually cool. So for this to happen, actually we need to have these computers in the LAN to be able to accept messages or packets from the broadcast. And so as long as this is 0, then they are actually vulnerable to this attack, and they're going to be able to send ICMP echo replies to this machine, to the victim machine. Now the way that we do this is by using the hping3 command, and it allows us to input here the destination IP address, which will be in this case the broadcast, and then the A flag is going to allow us to spoof the IP address as that of the victim, which is this Ubuntu 16.04. We're going to be sending an ICMP packet using the echo request, which is number 8. We're going to use a debugger mode, and then we're going to flood it. So the way that this works is, the way that we're going to see this happen is by using iptraf-ng, which will allow us to actually monitor the traffic in real time. So we're going to we're going to take a look at EMP0S3. So now here we're going to see, if we stop the attack, that yes, we are actually having echo replies that are coming from 10.02.14, which is this machine, and we can also see that we're having also ICMP echo replies that are coming from the server 10.02.10, and as well obviously as this server itself, right? This is actually sending echo requests, right? Not echo replies. And so how do we prevent this attack? And before actually preventing the attack, let's also take a look at the CPU utilization pretty quickly. And we're going to see that the CPU utilization is going to be even greater, obviously, the more machines that are connected in the LAN, right? And in this case, there are only 2 machines. So how do we prevent that, or at least mitigate it to some degree? Well, we can actually set the broadcast to 1, and so what this means is that we're going to these servers are going to be ignoring the packets that are being sent from the broadcast, right? We're going to do the same thing for this machine. So this is going to be 1, and now they are actually configured to prevent accepting packets from or ICMP packets from the broadcast. If we conduct this attack again, and if we use iptraf-ng again, we're going to see, well, that the only machine that is actually sending echo requests is actually the server machine, or the victim machine, right? Because we have spoofed its IP address, right? Now, how can we see the impact on the CPU? Or actually, let's see the impact on the CPU utilization. And we're going to see that it actually reduces basically to the third, actually half, basically. So it's 37% is not 60%. Now, we have tried, honestly, all of the possible mitigations using IP tables, UFW, and network file configurations, but we were not able to prevent an attacker from spoofing the IP address as that of the victim and prevent the victim itself from sending ICMP echo requests to the broadcast. Like, there was no way that we could do that. So this mitigation works partially, but it's not perfect. So what we're going to see now is the charging attack. This charging attack is going to happen at a transport layer, and basically is about this attacker server is going to be sending TCP or UDP packets to reflective servers that have the open the port 19 open, and that have obviously the charging server enabled. So for us to tell, right, if one of the servers, for example 10.02.14 and 10.02.10, have open ports, then we obviously need to take a look at with Nmap if the port 19 is actually open for TCP and UDP protocols, and actually it is for both of them. And we can do the same thing for 10.02.14, and we should get the same response. So once we acknowledge that, then what we can do is now start doing the attacks, right? So I already have the commands in here. So this is going to be using again hping3, and we're going to be using this server in here as a reflector charging server. and we're going to spoof the ID of the victim, which is this Ubuntu 16.04 machine. We're going to be using the port 19, and we're going to be using in here, we need to be careful though, we need to be using UDP packets. Okay, so it's UDP protocol, and we're going to flood the server. Now the way that we are going to be able to see this thing is by taking a look at the packets that are being sent. So if we start with here, we're going to see that here we have the UDP packets in red, right? And so we can see honestly that the capture UDP packets are actually not that many or not plenty. So based on the experimentations that we have made, the charging, so the charging attack is actually not that strong unless we have too many or many actually reflective servers. And so we can also see in here, if we go to the general statistics or not to the statisticals break, is the detail interface? Yes, it's in here. We should also see the incoming packets in here, right? So these are the total rates for incoming packets and then also outgoing packets. Now we are going to have to stop this attack, but before stopping this attack, let's also take a look at the resources in terms of CPU utilization that's being used. And we're going to see honestly that is not that big of a deal. Actually, to be honest, at most we're going to see a 0.7% of the CPU utilization being used, and it is just because this is not receiving too many let's say packets in a short amount of time. That's basically the reason. Now the way that we can prevent this attack from happening is by configuring the charging servers. Now there is a network file in Ubuntu servers that will allow us to do so. So in here what we need to do is to go to the etc folder, and in here we're gonna have like many folders and files. So what we need to do is actually to grab the folder that is related to net, and specifically that should be the signet d.d. So what we want to do is to go to signet d.d, and then from here we're gonna be able to see many services. Services, and so we can go ahead and use Nano to open the charging server. And interesting enough, there's no content. That's weird. Let me see though. Being charging server. Okay, that was weird. So we're gonna actually edit this thing to make sure that it is actually disabled. Okay, both the servers for internal and for UDP and TCP protocol. So we're gonna disable both of them. We're gonna save those changes in here, right? We're gonna do the same thing for these other servers. The last thing for us to do is just to make sure that we actually update kind of like these changes. So we're gonna use this following command, and what this command will do is to make sure that those changes are actually saved. So we're gonna use insert netd, right? And we're gonna do or run the same command in here. If we do that, then we should be able to tell, even without attacking, that the charging port should be closed, because there is no service being listened at port 19, right? And so it's closed for 10.02.14 IP, and then for also the IP 10.0.2.10, right? Those ports should be closed for both of them. If they are closed, then obviously, if we take a look at IP traffic here, and in the that will be the detail interface for this interface, we're going to see that these attacks are actually or should have no impact at all. You see, so the bits or kilobytes per second that are being sent, I think, are most likely related to basically these ICMP requests that are not getting to this server. What we already see that the UDP packets are not being sent. Okay, the next attack that we're going to be covering is called the LAN attack, which is local area network denial, and also going to cover a little variation of it, which is the well-known SYN flood attack. So the LAN attack basically works by spoofing the IP address of that of the victim, and also making sure that the destination IP address is also the same as the victim. So the victim basically is going to be sending literally SYN packets to itself, and so it's going to be stuck in a loop. So the way that this works is by doing the following thing. So we're going to start with top, and then we're going to enter this command in here. So in here we're also using hpin3, and then we're saying, okay, the destination port is going to be that of the victim, and then we're also going to spoof the IP address as that of the victim. So we're going to be stuck on a loop. We're going to use the flood flag and then the S flag, which stands for SYN packets, and we're going to be using an open port, which in this case is the open port of the web application, right, which is port 80. If we do that, then we should be able to see a CPU utilization in here that is quite low, but still it's impacted. If we take a look here at the traffic, then we will see that in here we have packets that are being sent and received from the same IP address. So that will be the way that the local area network denial of service works, or the LAN attack works. Now, when it comes to the SYN flood attack, it is very similar in the sense that we're also using hpin3 and flood and then the S flag and then P80, but we're sending these packets from the source IP address, which is in this case 10.0.2.4. So I'm just going to show the config here. This is the IP address of the attacker machine, right? So that is what's going on. Now, if we do that, then we're going to be having a greater, let's say, impact on the CPU resources. And it can go, actually this can go pretty high, even higher than 40. I've seen that. So the way that we can mitigate this attack, and basically before going there, we also can take a look at here, right? We're receiving packets from 10.0.2.4. Now, the way that we mitigate this attack, and we're going to stop it, is by also configuring the IP tables. Though the configuration or the mitigation is not perfect, I would say, but still it's decent. Now, the way that we do it is by entering the following command. We're going to be using IP tables like so, IP tables, and then we're going to say, we're going to insert an input. Basically, this basically inserts a new rule for inputs, where we're going to say that the source IP address, which is 10.0.2.4, we are going to say that any TCP connection coming from that IP address, we're going to want to drop it. That's the first thing that we want to do. Now, after that, we also want to limit the number of SYN concurrent requests that are being made per second. So we can also use IP tables here and say that now we're going to append also a rule for the input, where any TCP packet that's coming in and that uses the SYN flag, we're going to limit it by one SYN concurrent packet per second. And so that is what this command is doing. And finally, we're going to go ahead and say that also we want to make sure that the input for a protocol TCP on port 80, which is the port of the running application, we'll also want to make sure that any SYN packet that's coming there, we're going to name this mitigation called SYN flood. And this basically means that we're going to limit the number of newly established connections for a single IP in 60 to 10, basically. So that means that we're going to use the update command here, and then seconds, we're going to say 20 here. And this will allow for the server to mitigate the attack, not in full, but it's going to be good enough. So we're going to start with htop here again, and we're going to try the SYN flood attack again. And we will see, obviously, that we're not getting to 30%, but we at most get to 9% or 5%. So in this video, I'm going to be talking about the fast HTTP attack. And the fast HTTP attack is also known as the HTTP flooding attack, and it happens at the application layer. And so basically what this does is just to send a burst of requests to the server using a TCP protocol and HTTP request. It could use actually any method. So for example, we can use get, put, post, patch, whichever, as long as we're sending them in bursts, like literally as fast as possible. Okay, so the way that we're going to be conducting this attack is actually super simple. We're going to have this attacking machine, which is the Ubuntu attacker running on 10.0.2.10 port, and then we're going to have we're going to see how this impacts the resources of this machine. So what we're going to do is that we already have a running application here, which is in here, right? It's running here, and so what we'll do is to start this attack, and we're going to take a look at the system resources. So in here we see that it's not being used at all. Now if we send the attack though, we're going to see that at some point it's going to hit near 100% of CPU utilization, but barely, or kind of like on average it will be from 60% to 100% CPU utilization most of the time. So that is what we see right there. Now there is another way to conduct this attack. This was actually based on HTTP GET request. So now we can use another one, which is HTTP post. And how do we use that? Well, what we're saying here is that we want to attack the server that is on port 10.0.2.15 to the endpoint API users login, which is an endpoint where we can do post requests. We're gonna make 999,999 connections. We're gonna have to create 500 connections per second, and we're gonna be using a file called attack data. Now, what is attack data? Well, attack data, if we use nano for attack data, we're gonna see that it is a file that has this string. Basically, it is the endpoint of the website where we do the login, the method that's going to be post, and then the contents, which is email and then password, because we already know as an attacker what are the parameters that this endpoint is expecting us to get. Okay, so that is that. And then we're now going to be using that file, that configuration, to send a post request. But obviously this post request will not create entities in a database, because obviously we're just using fake data. What we only want to do though is just to literally kill this application, right? If we're doing that though, and we're near 100%, then we should see a delay in the response time, right? But obviously this is not happening, because the only way that this can only happen is if we were to be using a distributed denial of service attack. Basically, websites are going to be very laggy when we are using 100% of the CPU utilization. So that is only the way that we're going to be seeing that. Now, how do we mitigate this attack? Well, basically I'm gonna leave htop there. I have here already the commands. I'm gonna use IP tables again. There are no roles yet here, but what we can use, and actually no, it's not here. I'm just gonna write it myself then. So basically the mitigation is super simple. What we're gonna say is that we're gonna be using IP tables, right? We're gonna say that we want to append an input rule any incoming packet using the TCP protocol. We want to match a certain state, right? That certain state is city state. For any new incoming connections, we want to limit them, and this limit is going to be of 60 connections per second, right? For each of the people, let's say that or for each user. And then what we say is that when we get a burst of requests, we just want to make sure that at most we get 20, right? And we want to accept that as a rule. Now, the last configuration is just to make sure that we also append another input for TCP packet or TCP protocol, using again a matching pattern for new connections, which is city state and then new. And then we just want to say we want to drop everything else. So what this will do basically is, by default, we're going to try to drop connections, but at the same time we're going to say that we also want to limit. We're going to drop by default, let's say, right? But we're going to say that for new connections, we're just going to limit the times that they can actually perform a request. So if we do that, we're going to see that the rules are added here, and then we're going to see the CPU utilization for both attacks. So this first one is going to be for the GET request. And what we're going to see now, that the CPU utilization is not going to go higher, I guess, than 30%. So it's going to stay pretty low. It's not perfect, it's not a perfect solution, but obviously it's going to stay pretty low. There may be some other IP table configurations that might be better. Obviously, if we were to limit the rate even lower, then we should get obviously a lower result. But we want to make sure, obviously, that the client is also going to be able to, to make use of the application, right? And the other attack is going to be based on post request. So this is the post request, and we're going to see how this impacts now the CPU utilization. And again, it should be less than 30%, and that is